Hello everyone, I'm Hani, and along with Christian and Yohanna will be presenting to you our project titled A Novel Intrabody Communication System with Optimal Electrodes on a Flexible Substrates. Now before we begin, I would just like to thank our advisors for their great support, and I want to acknowledge that this project is in collaboration with the University of California, Irvine. Now imagine a world where your health is continuously monitored. While this might seem as a luxury at first, continuous health monitoring is starting to present itself as a viable solution to many of our problems. If your health was continuously monitored, this would minimize hospital visits and therefore cut costs for both the patients and the healthcare system. It would also reduce medical disorders such as strokes and heart attacks, and finally, it can even provide personalized training plans for athletes. Such a great demand for health monitoring has been unsurprisingly paralleled in an explosion in the wearable devices market. In fact, by the year 2030, it is projected that we will be using more than 2 billion wearable devices. Such a great demand for wearable devices in turn shows many different challenges, and one of these would be to connect all these different wearable devices to one another and to a central processing unit such as your smartwatch. So for example, you could have a glucose sensor on your arm that needs to communicate with an insulin pump that is on your stomach, for example. So one way to do that would be to use traditional RF waves such as Bluetooth. We could also use ultrasound waves, we could use electric currents, electric fields, and even magnetic fields. But IBC is in reality the use of electrical currents or electrical fields. But what is IBC, or intrabody communications, you may ask? Well, it is a technique that uses the human body as a transmission medium for electrical signals to interconnect devices in wireless body area networks. So as I said, IBC has two main types. We can either use electric fields, and this would be called capacitive coupling, or we can use electric currents, and this would be called galvanic coupling. And the way galvanic coupling works is that you would have two electrodes for the transmitter attached on your skin and two electrodes for the receiver. By applying a differential voltage on the transmit electrodes, this would cause an electric current to flow through your body and reach the receiver electrodes. Now, why not use, for example, Bluetooth or other RF technologies? The reason behind that is because galvanic coupling IBC is extremely low power, which is very important for wearable devices. In addition, since the signal is confined to your body, there is very little radiation and interference, in addition to high security. So what we propose is a novel end-to-end galvanic coupling intrabody communication system composed of electrodes that we design, in addition to the transceiver, which consists of an analog front end and a back end, which we are going to be implementing on an FPGA. But why should you really care? And why is what we're doing both important and exciting? Well, for several reasons. First, our IBC system is completely compatible with IEEE's physical layer for IBC, which means that we'll be operating at a frequency of 21 megahertz. 90 to 95% of IBC transceivers do not adhere to this IEEE standard. Number two, we're using BCH error correcting codes, and while these codes have been used extensively in other RF transceivers, we claim to be the first IBC transceiver who are using these kinds of codes. Number three, we're designing our own flexible electrodes that are optimally configured. Now, what papers out there do is that they either use commercially available medical electrodes, or they study some electrode configurations, but with the end goal of modeling the human body, and not with the goal of actually fabricating or designing this electrode, which we are doing. Number four, by developing an end-to-end system, we are able to really deliver on the best performance. Now, ideally, we would like to have the whole transceiver built on top of the electrode itself, so all of them will be on one substrate. But this would require the development of an application-specific integrated circuit or an ASIC chip, and for time constraints, of course, we do not have the capability to do that, so we suffice by only integrating the analog front end on the electrode and then the back-end circuitry will be implemented on an FPGA. In addition to that, while capacitive coupling IBC have been around for a really long time, galvanic coupling transceivers are a much newer research thrust. Therefore, there is much less literature on galvanic coupling. So anyway, also we're trying to add to the work in galvanic coupling in literature. So as I said, our IBC system mainly consists of the electrodes and the transceiver. So I will start now talking about the electrode design. So electrodes usually used in literature for IBC or for galvanic coupling IBC are either these medical electrodes, which are commercially available and are usually disposable, or some sort of copper or silver electrode, but really with no design justification. So these are what is used currently. There are also other interesting electrodes, but not really for IBC, not really for galvanic coupling. These are mainly used to monitor biological effects such as ECG monitoring. So to start with our electrode design, we should really start with a model for the human body, because really we're designing something on the human body. And it turns out that we have three different models. We can have electric circuit models, electromagnetic models, or even physical models. And the reason we have all these different models is because the human body is a very complex medium. It has a complex permittivity and a conductivity that changes with frequency. In addition to that, each one of us has a different body composition, adding to the difficulty of the modeling. So electric circuit models, for example, although they're not accurate at high frequencies, they yield analytical expressions for body attenuation, and therefore they are used in the design of the transceiver. Electromagnetic models, they utilize numerical techniques such as the finite element method, and therefore we design them to design our electrodes. And finally, phantom models allow experimental measurements to be done without any physical constraints, but they're limited to a single frequency and not very useful in our case. So we start with the electromagnetic models designed on ANSYS HFSS, and we use two models. We have the full body model and the multi-layer dielectric block model, which consists of several layers of human body tissue. Now, we try to see the difference between these two models, and if we simulate the same electrode on both of these models, this is what we get, for example, for the reflection coefficient. As you can see, there is a difference between the two. Ideally, they should be identical. But here we're looking at 300 gigahertz. If we zoom into 100 megahertz, we see that the difference is not very significant. Okay, and we're interested in this range. So what we do is that we start with the dielectric block model because it's much easier to simulate and design electrodes on. And for example, these are the different thicknesses of the different layers. So we want to design this electrode, but really what are the different parameters that we can design? Well, there are many different electrode parameters. We can try to study the effect of the electrode area. We can look at the inter-electoral distance. We can look at the channel length, the transmitter's power level. We can look at different feeding configurations or feeding positions. We can look at different electrode shapes, square, triangle. We can look at the transmitter's output impedance, the electrode material, or even the electrode skin interface, or the presence of a certain gel. So, okay, we have all these parameters to study, but in the end, what are we really looking at? And it really comes down to S parameters. We really would like to minimize our reflection coefficient to achieve a very good match to the skin. We want to maximize our transmission coefficient, or in other words, minimize path loss. And finally, we want to minimize our specific absorption rate, and this would minimize the losses and also allow us to adhere to certain standards, such as the FCC standard, which limits the SAR to be below 1.6 watts per kilogram. So, starting out with the electrode area, for example, here I'm showing 3 different electrode areas, 4, 9, and 16, and for 2 different shapes. And as you can see, increasing the area allows us to achieve a better reflection coefficient. Another thing to note here is that even though both shapes have the same area, they have different reflection coefficients. Next, we study the Inter-Electoral Distance. So this is the distance between the two transmitter electrodes. And here we simulated it for 8 different distances and for different output impedances. But if we only keep an output impedance of 125 ohms, for example, we see that increasing the inter-electrode distance allows us to achieve a better reflection coefficient. In addition to that, the transmission coefficient is also improved as we increase this distance, and this can really be explained using the galvanic coupling IBC equivalent model. So if these are our transmit electrodes, it is a well-known fact that most of the current actually flows between the two transmit electrodes and not to the receiving electrodes. So by moving them apart, we really allow this current to flow to the receiver. Next, we study the effect of transmit power, so how much power we're pumping into this electrode. And it really turns out that there is a linear relationship between the transmit power and the average SAR. So increasing the power, say, by 10 times would increase the average SAR by 10 times. And by doing some calculations, we reach a conclusion that the maximum power that we can pump based on the FCC standard is 120 milliwatts in our case. Next, we study the effect of channel lengths, so moving them apart. And as you'd expect, as the transmit and receive electrodes move further apart, the transmission coefficient, of course, decreases, and it actually shows a log relation. Next, we study different feeding configurations. So where we are feeding the electrode, we can feed it from the center, from the inner side, from the outer side, and there are many other different configurations. We tried that for many different shapes. And here, for example, I'm showing the square. This is the reflection coefficient for the square for 3 different configurations. And as you can see, the reflection coefficient changes. But we cannot really generalize that one configuration is better than the other. This really depends on the shape. We also try feeding the electrode from the top and from the side, and we get these results. Next, we tried 7 different electrode shapes. All of these have the same area, everything is the same, only the shape is different. And what we do is that we sweep over S11, S21, and the average SAR for all these different shapes and for all the different configurations. And we come up with these 2 figures of merits, which we wish to maximize, and then we try to maximize them at the whole frequency range. And it turns out that the triangle with sharp inter-edge achieves the best performance based on both of these figure of merits. Next, we see the effect of the output impedance of our transmitter. And as you can see, by changing the output impedance, for example, from 50 plus J100 to 50 minus J100, we can see how the reflection coefficient can be moved around in frequency. This is only by changing the output impedance of the transmitter. Next, we study different electrode materials and confirm what the literature says, that different electrode materials do not influence much the performance whenever a conductor is used. And finally, we study the effect of an electrode skin interface. So this is basically the presence of a certain gel. And it really comes down to a trade-off between SAR, where an air layer would be better, or the transmission coefficient, where using a gel layer would actually give us a better performance. So next, Christian will talk about the transceiver design.
بس بتذكرني اسمك لو سمحت.
Hani.
Okay, so on our